Okay, welcome back to the workshop. Hopefully by now you've been able to load up this notebook. And what I'm going to suggest people do is actually to go over here and make a copy of that workbook and open up that copy. And got to wait for it to load up here. Okay. And then go here to kernel and restart and clear all outputs. So this way we can work with a clean notebook, but we can still refer back to the previous one if we want to see a fully worked out notebook. So in this notebook, what we're going to do is we're going to take some data, train a model, and then we're going to look at the calibration of the model, see if it's well calibrated or not, and then we're going to explore various methods to calibrate the results of these models. This notebook requires NumPy, Pandas, scikit-learn. Most people should probably have those installed in the environment they work in. And then you'll also need the ML Insights package and the BetaCal package. So let's get started. Just do a bunch of imports. Please check that your ML Insights version is at least 0.1.6. And let's talk a little bit about the data we're going to use. So this data is from the Mimic ICU data set. So each row represents the hospital stay of an individual patient. And the data includes lots of lab value and vital sign measurements of that patient during this stay in the ICU, and also has an indicator of whether or not the patient died in the hospital. So we're going to be building models about predicting mortality for patients in the ICU. Here's the reference of who built this data set. So let's go ahead and load this in. And then this data actually has a lot of missing values. So to kind of simplify the presentation, I'm just going to impute the median for each of those. It's not always the best strategy, but in this case, just to illustrate the calibration, that's what we'll do. Let's run that cell. Okay, so lesson 1 is going to be about assessing the calibration of a model. So how do we know if the model is well calibrated or not? How do we know if the probabilities are behaving like probabilities or if they're really just kind of numbers? So to start, I'm gonna just pick 6 variables. It's actually 3 different, 2 lab values and 1 vital sign measurement. So this is BUN is the blood urea nitrogen, and we're gonna have its minimum and maximum value. WBC is the white blood cell count, again, minimum and maximum, and CysBP is the systolic blood pressure. And these are just 3 variables. Again, the idea is just to build a model so that we can then see is it calibrated or not. So now we've got an X that has our features that we're going to use to predict, and we've got a Y which has our response. Our response is this thing called hospital expire flag. It means whether or not the patient died during the course of the hospital stay. And so to move forward, we're going to start by dividing the data into training, calibration, and test sets. So we're going to use the training set to build the model. We'll use the calibration set to calibrate the probabilities, and then we can evaluate the performance on the test set. Later, we're going to learn about cross-validation approaches that avoid the need for a separate calibration set. So one downside of doing calibration this way is you have to set aside some data for calibration. That means you have less data to train on, which you always want to train your model on as much data as possible. And down here in this cell are the controls to set what percentage to use for training, what percentage to use for calibration, and then the test percentage is just whatever's left over. And this RS is the random state that we're going to use. And this random state is both for generating the test splits and also for the random forest creation. One thing to note is that there's actually a lot of variance in performance between different trained test splits. Just changing the random state, you might have one calibration technique does better than another. So you don't want to draw too many conclusions from individual runs. At the end, we're going to play around with, running this over and over again and trying to observe what changes and what patterns you might see. But just something to keep in mind, don't say, hey, this model did better than this model on this run, so therefore it's better all the time. It's not quite that simple of a picture. Okay, so let's go ahead and run this cell. And then these next 2 cells I call train test split twice to divide it into actually 3 different sets. And I'm starting out using 60% of the data for training, 0.05 for calibration, which leaves 35% left over for test. You want to leave a fair amount in the test set so that when you're comparing the different calibration models, you have a lot of data to compare them against. Okay. So moving forward, one thing I always like to do before I build a model is just check, this is a binary classification model, and you always just want to check what's the kind of baseline probability overall on average, what percentage of cases were yes versus no. And so here we see 10.9%, so 10.9% of the patients died in the ICU. And this gives you a sense of how balanced your data is, and it also gives you a baseline to compare, if 30% means you're more likely than average or less likely than average to die. So in this case, if you're 30% likely to die, that means you're one of the sicker patients in the ICU. Okay, next we're going to fit a random forest model, and then we're going to use that model to predict probabilities. And we'll see that random forest, it's not terrible, but it's not always great about calibrating its probabilities. So the percentage, the probability it gives out is the percentage of trees that voted yes versus no. And you shouldn't in general expect these to be well calibrated. The fact that 60% of the trees voted yes doesn't necessarily mean that the case has a 60% probability of mortality in this example. So we're going to build a random forest, 500 trees, use this balanced subsample since we're a little bit unbalanced, and specify our random state here. I'm going to fit that model. And then we're going to call this predict proba, and I'm going to take the column 1, remember it's 0, 1, so this is the column that indicates what's the probability of death, of mortality. Okay, so how do we assess calibration? And there's lots of different ways people might think of to determine whether the model is calibrated and whether you've improved your model or not. The metric I like to use is generally the log loss. So you may have used the log loss before in fitting models. It's also called the cross entropy. If you come from a stats background, this is basically the negative mean log likelihood of your data given the model. And so it's a common metric to measure the quality of predicted probabilities. Now, if you've worked with binary classification before, you might also have used the AUC, the AUROC, the C statistic, the area under the receiver operating characteristic curve. And the thing with the AUROC is that it measures the quality of the ranking, but it does not assess calibration. It does not tell you anything about whether your probabilities, when you said 20%, did that really mean 20%? Whereas the log loss does. The log loss will penalize you if something happens 30% of the time and you said it only happens 10% of the time, or vice versa. So log loss assesses the combination of discrimination. Discrimination means, are you able to make different kinds of predictions about different kinds of cases? And calibration, which means, are your probabilities accurate? You can have a very well-calibrated model. In this case, we could have a very well-calibrated model by just saying everyone's going to die with probability 10.9%. It would be very well-calibrated, but it wouldn't be very useful because it doesn't really discriminate between patients. It doesn't recognize that some patients are more likely than others to die. One reason why people don't like using the log loss is because it's difficult to interpret on its own. There are meanings to it that involve entropy, and those require a bit of information theory and thinking to really understand well. But just to give the definition real quick, the log loss basically says if you've got a positive case, I'm going to take the log of the probability and negate it. Because remember, the log of a probability is going to be a negative number, so we want to work with positive numbers. So we're going to treat it as a loss. We're going to take the log of the probability of what happened. So in the positive cases, that means if we said someone had a 30% chance of dying and they did die, then we want to say that take minus log of 0.3. If we predicted someone was going to die with probability 30% and they did not die, well, then what did happen was they survived, and that event had a probability of 0.7. So we want to take 1 minus the probability in that case. So for each case, we take the log of the probability of what happened, and we add them all up, and we take the negative and we take the mean. So actually I missed something here, which is I should have a 1 over n over all of this. So I will correct that in the notebook by the time you see this, but it's wrong in my notebook right now. So if you predict the probability of 0.25 for a case and it happened, your loss for that case would be minus log of 0.25, which is the same as log of 1 over 0.25 is log of 4. If we predicted probability of 0.8 for a case and it didn't happen, your loss would be minus log of 1 minus 0.8, blah, 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 would be log of 5. So basically, you get a bigger loss when you assigned a smaller probability to what actually happened. You get a 0 loss if you were certain and you were right, but you get an infinite loss if you were certain and you were wrong. So you generally don't want to predict 1s or 0s, because if you're wrong, that one mistake will outweigh everything else you did on anything else. Okay. So we built this model. Going back, we built this model. We made these predictions. Let's evaluate how we did both in terms of AUC and log loss. So the AUC, we got 76.4. It's reasonable. Definitely has some discrimination power. And our log loss is 0.312. We don't really know what to make of that, whether that's good or bad, or what to think about that. But to illustrate what I was saying before about that the AURC just measures the quality of the ranking, but not calibration. Suppose I divide all the probabilities by 4. So I'm going to take this divided by 4, this divided by 4. And you see that I get the exact same AURC. AURC does not really care. It just cares about the relative ranking of the different cases. But we see that the log loss got a lot worse because these probabilities, presumably when I divide them by 4, now they're systematically probably much too small. So we see a big penalty in the log loss. Another metric to assess calibration is what's called the Briar Score. And the Briar Score is basically the mean squared error between the predicted probabilities and the true answer. So if I predict 0.7 and the case happened, my error for that case is 1 minus 0.7 squared. And again, I missed the 1 over n here. This should be the average, the sum of all of those things divided by the total number of cases. And again, I'll have that fixed hopefully on the notebook by the time you see it. So average this score on all cases, that's the Briar Score. The key difference between Briar Score and log loss is that the worst case for Briar Score is 1. I mean, if you said you were certain it was yes and it actually ended up being no, you get a bad penalty, but it's 1. It'll kind of get lost in the shuffle out of if you had 20,000 data points and you made one really bad mistake like that. It'll kind of won't make that big a difference. But for log loss, that's going to be infinite. It's really going to punish you for being overly confident. And where this makes the biggest difference, so moving on to this next cell. So let's just go, let me pause for a sec, run through the Briar Score. So the Briar Score loss is 0.0849. And, one way to think about that is, right, if I was off by 0.3 on average, I would have 0.09. So I'm off by a little bit. I'm off by less than 30% on average. Now, log loss versus Briar Score. The main difference, again, is that when you look at really small probabilities. So suppose if the true probability is 1% and you predict a probability of 0.0001, so 0.01%, so 1 in 100 versus 1 in 10,000, is that a big error or not? That's the question you're trying to answer, and it really might depend on your application. So according to log loss, that's going to be a very big error. You've understated the true probability by a factor of 100. So if you're working in insurance and you said only 1 in 10,000 of these people is going to have an accident, and actually 1 in 100 of those people had an accident, you'd be paying out 100 times as much on those people as you thought you would, and you'd probably put the company out of business. But for Briar Score, that's not a big deal. It's 0.01 minus 0.0001 squared. So it's really a tiny error. So for some applications that might be appropriate. So for example, if you're working in politics and you're trying to model the probability that someone's going to vote for candidate A versus candidate B, and then you're going to use that model to apply to some population and say what you think the election results are going to be. It actually doesn't matter to distinguish between very low probabilities. Whether someone's very unlikely to vote for the candidate or very, very, very unlikely to vote for a candidate doesn't really make much of a difference to your use of the model. So this is actually a very deep topic. There's a lot to think about here about rare events and the order of magnitude of rare events. In this workshop, I'm going to focus primarily on the log loss, but we'll also show results on the Briar Score. Okay, so we have these two numerical measurements of calibration. And now we also want to have a more qualitative one, just a visual way to look at the calibration model. And this is what's called a reliability diagram. And the idea behind the reliability diagram is you want to know when somebody said 5%, was it really 5% of the time? So I'm going to make bins around 5% and look at all the times my model predicted something pretty close to 5%, and then compare what actually happened to what my model predicted. So let's say I bin the interval into these 20 bins, and I find the empirical probabilities. So I look on my test set, how many times did this occur, and what percentage of them are yes and no. So if there were 20 occurrences that fell into a bin, 9 of them were yes. That means that the empirical probability is 0.45. And then we're going to plot the predicted probability versus the empirical probability. So what we thought the probability was versus what the actual probability was on the cases that we saw. And if everything's perfectly calibrated, we should expect to be pretty darn close to the line y equals x. And if the points are above the line, we're under predicting the probability. The true probability is higher than what we thought it was. And if it's below the line, we're over predicting the probability, where the true probability is less than what we thought it was. So to plot these reliability diagrams, we're going to use a function in ML Insights. It has a lot of flexibility, and we're going to use some of the features. Some of the features that you can use custom bin widths. You could show the histogram on the side. It has error bars to say when you're far from the line, whether that's just a result of having not many observations in the bin. And it also lets you do this Logit Scaling thing, which helps you explore calibration at very small and very large probabilities. By very large probabilities, I mean close to 1. So I'm not going to go through all this, but you can see there's quite a few different options in this reliability diagram, and we explain them here. And I'm going to go through them over the course of this this workshop, so you don't need to read through it there, but just thought I'd put it there for reference. So for the default plot, we just do plot reliability diagram of the true 0-1 outcome and what the model's predicted probabilities were. So let's do that. So what we see is the line y equals x. We see the dots, some are below the line and some are above the line. And we have the error bars, so we can kind of see how big of a mistake it was. So within the error bars means something you'd expect to see about 95% of the time, if it was truly calibrated. So if the true probability was here, about 95% of the time we'd expect to see something in this range. So when things are outside that confidence range, that means that it's likely to be poorly calibrated there. And similarly, if you see several bins in a row where the error trends in the same direction, even if they individually are all within a confidence interval, that's probably an indication that it's making a mistake there. So here, the fact that we have like these 4 or 5 in a row that are below the line, and this one's totally out of the confidence interval, these two are right on the edge, that probably means we're over predicting the true probability here. So between about 2 and like 0.4, 0.45, we're over predicting the mortality. The true value is, the true probability is less than what we thought it was. The other thing to notice is it's really hard to see here. These points look really close to the line, but these error bars are really tight also. So it's hard to get that, and we're going to show later how we can explore what's happening at the tail better. So let's look at some other options in this plot reliability diagram function. You can have a histogram on the side which show the counts in each bin. So that's using this option, show histogram equals true. Plots a second plot where you see the bin counts. And this is important to give context to this picture because you see that most of the 8,000 plus of the data points are in this first bin. So, if we're making mistakes out here, there's actually not that much data and it's not going to hurt us that much. Whereas in these bins, there's a lot more data, so making a mistake will be more costly. So another reason why this is helpful is we might want to, when we have a lot of data, we might want to split the bin up to examine the calibration at the different intervals more carefully. And when we have very little data, we might want to aggregate the bins a little more. And so that's what we can do with this next cell, is I'm going to make a new set of bins. I call it custom bins A. And I'm going to say it has to start at 0 and end at 1 and be increasing in between. And I'm going to say I want to look between 0 and 0.01, 0.02, 0.03, 0.05. So I'm breaking up this big bin into 5 different bins. And then keeping the next bin the same. And then I'm aggregating bins from there on out so that we have a little more data in them. And so here we can see again a little closer, we have these 2 bins in a row where we're over predicting the probability. Actually, these 3 bins in a row where the dots are below the line. And then if you look closer over here, it looks like we're a bit over the line. It's really hard to tell though. And here we see the histogram of the bins, and it looks a little weird because the widths are different. So you see these very small lines, but you can see that we have over 1,000 points in all of these first set of bins, and then it's only these last 2 where we have less data, and even this one we probably have a couple hundred, so that's not bad. Okay, so I want to examine what's going on here better at these very small probabilities, and there's an option here to use what I call Logit Scaling. And without getting into too much of the math, the idea is really just I'm going to take this curve and kind of stretch it out. So I'm going to stretch the ends and move them closer to 0.5 so that I use more of the area of the plot to examine here and squish these guys together. And I made it really big so that we can really zoom in. So I made the figure 10 by 10. And now if you look at the scale, you see that out here it's kind of like a logarithmic scale on the ends. And then we're smushing together the stuff close to 0.5. And here if you zoom in, you see that we are way off on these very small probabilities. That we are predicting, when we're predicting very small probabilities, in fact, the probability is quite a bit bigger. So at the very low probabilities, we're under predicting. And then when we get to these probabilities over here, we're over predicting. One other point, I changed this marker to dot. That's just a way to make the dots a little smaller so that they don't take up so much area. Now, if I want to get into the numbers, I've been just kind of looking at the chart. I want to know what numbers these actually are, what's going on with these actual numbers. You'll see that I assigned, when I did this plot, I assigned it to a variable RD. And that RD actually has some of the numbers. So if we look at it, it's a dictionary. So this function returns a dictionary. and it has three things in there. It has the predicted probabilities, the empirical probabilities, and the counts in each bin. And so we can just print those out. And so, for example, in the smallest bin, we see that we have about our predicted probability of the points in that bin averaged out to about 0.0017. But in reality, there was about 1.23%. So these numbers are a little bit off that I write. So let me just fix this. Of about 0.0017, but empirically on 3,089 trials, we have a probability of 0.012. And so if you see 0.0017 divided by 0.012, I should do it the other way. 0.012 divided by 0.017, it's about a factor of 7 I'm off by. So again, this gets at this issue sort of between log loss and Briar Score. For the log loss, this will be a big issue because I said the person had this probability of death, but they were actually 7 times more likely than I said they were to die. For Briar Score, it wouldn't make that big a difference. You'd just say the probabilities on the absolute scale are very close to one another, so we don't really care that much. Okay. One thing I want to point out is sklearn, scikit-learn does have a calibration curve function. It's pretty basic. We can kind of do a shift tab. You give it, again, just like this one, the true y's and then the probabilities. And you could give it a number of bins, and then there's 2 ways it'll divide it into bins. But basically, it just returns these same numbers that I had in my first 2 bins, the pred probs and the imp probs, and then leaves it to you to plot with them. So it doesn't do error bars, doesn't do custom bin widths, and so forth. But I want to let you know, it is there. There is a scikit-learn way to do this curve, but it's a bit more basic. Okay, so we're going to stop now for the first exercise, and what I want you to do is to repeat this process for a bigger set of features below. So if you uncomment these next few cells, you'll see I'm going to make a bigger feature set called feature set 2, where I take the features in feature set 1 and add a bunch more. And we're going to repeat that train test split, train calib test split, fit a new random forest model, RF model 2, make the same predictions, look at the results, and then I want you to plot some reliability diagrams using some of the functions that we had up here. So we'll take a pause here. And then let me just say, then if you have time, you could try fitting another kind of model, like a boosting a logistic regression model or something on the same data and assessing the calibration of that model. So I'm going to pause here in this module and give you about 5 or 10 minutes to work on this. And then please resume with the next lesson.